get nothing interesting. But what is amazing is that if you restrict the operators, these operators in this class, to a two-dimensional space consisting of the eigenvector and its derivative, you get something amazing, namely the 2 by 2 matrix representation of this operator with respect to an orthonormal basis obtained by the Gram-Schmidt orthonormalization of the eigenvector gamma omega and its derivative gamma prime omega actually is the curvature in the sense of complex geometry. Then we showed that if the operator is to be a contraction, then of course these 2 by 2 matrices that you obtain by restricting the operator, they also have to be a contraction. And that leads to an interesting curvature inequality. While discussing all this, I did mention the questions of representing an operator, finding a model for an operator, and also finding invariants for an operator. And we said that the curvature that you get in this little 2 by 2 matrix after restricting an operator in the Cowan-Douglas class is actually an invariant. In the case where the dimension of the eigenspace is actually 1, this is not only an invariant, it's actually a complete invariant. Now, I want to continue with the same theme. Actually, I left off. So here today, for example, I have said I should begin by finishing off what I did not do yesterday. And obtain a curvature in which we have seen a curvature inequality, namely that here again I'll write norm t lesser or equal to 1 means that the curvature of this operator t at omega is lesser or equal to 1 over 1 minus absolute omega square whole square with a minus sign. This is the curvature inequality, and this, if you like, is the curvature of what I call the backward shift. So in that sense, this backward shift is an universal object. It actually is the upper bound for any contraction, the curvature of any contraction. So now, just for those of you who wish to pursue such things in future, I would like to point out some directions of research that remain open even today. One of the things is to try and consider or ask such questions involving this is a contraction, whereas one could talk about multi-connected domains. Here it is a contraction, means that the operator is in what is called V1 of D, open unit disk. But if you take a T in V1 of omega, then you can ask for curvature inequalities like these, and you can ask for whether there is a universal operator like the backward shift operator here that bounds the curvature of operators in V1 of omega, satisfying appropriate hypothesis which has to substitute this condition contraction. Okay, that's one thing. The other thing which is of great significance and hasn't been answered yet is, first of all, I did say, and it is true, that the curvature is a complete invariant. And this means curvature of T is equal to curvature of T tilde is equivalent to, for all omega in capital omega, T comma T tilde in B1 of omega. So you have two operators in B1 of omega and their curvatures are equal. Then the Cowan-Douglas theorem simply says that T is unitarily equivalent to T tilde. So then you expect that the contractivity of an operator T in B1 of D must be determined, must be characterized by the curvature. So this is the reason why we start even thinking about curvature inequality. One way we have seen that if T is a contraction, then this implies that the curvature of T at omega is lesser or equal to this quantity. But what about the converse? If you have such a curvature inequality, then does it follow that T is a contraction? Now that's a very serious kind of open question. Partial answers are known, but there is really no characterization yet of contractivity purely in terms of curvature. So that's something that those of you want, you can think about. And as I said, these are, the discussion of commuting tuples of operators, keeping in mind these curvature inequalities and such, is another area that remains full of open problems like this. What I'm going to do today, like yesterday's main point was how Gram-Schmidt is sort of gives rise to curvature. This is what we saw, or at least I hope I convinced you of this. This I somehow find very, very pretty kind of thing. All the discussion that involved finding a model for the operator T in terms of a non-negative definite kernel, or what I called a reproducing kernel, which was discussed later at some length by Deepak in the afternoon, and he will continue a little bit of more discussion on that. What is left from yesterday would have been to try and write a curvature inequality in a stronger form than what I discussed. The reason we want a curvature inequality in a stronger form is that we know the inequality curvature of T omega lesser equal to minus 1 over 1 minus absolute omega square whole square. This inequality does not imply, this is too much of a weak inequality, does not imply that. So if you have T in B1 of disk such that curvature of T this does not imply that T is a contraction. So this does not happen. Consequently, one needs to a strengthening of the inequality may force contractility. And that is the reason why I would have liked to discuss this. But this is only a further discussion. There is no, I mean, one can do it, but it is not essential at this point. Looking at what I have to discuss today, I would much rather first finish another way of looking at these relationships of the curvature and kernel functions and so on and so forth with complex analysis. And if we still have time, I'll come back to the discussion of what remained unfinished yesterday. But at least I did finish with a curvature inequality for contractions and pointed out that the Gram-Schmidt orthonormalization actually gives a relationship with curvature. So today, the main goal is to say, all of you know that by the Riemann mapping theorem, any simply connected plane domain not the entire, which is not the entire complex plane, is biholomorphic to the disk. Now, this biholomorphic simply means that omega is a plane domain, simply connected. You have the Riemann mapping theorem says that there is a holomorphic map from omega to D such that F is bijective. In other words, F is bijective, but moreover, in this case, F inverse, which maps the disk into omega, is also holomorphic. This follows. Okay. Now, in view of this, one might wonder what happens. If we consider two simply connected domains omega 1, omega 2 in C2. Are they necessarily biholomorphic? Now, this question already occurred to Poincare, and there is a proof due to Poincare saying that the Euclidean ball and the polydisk are not biholomorphic. Now, just for the record, let me say the Euclidean ball is Z1 comma Z2 such that Z1 absolute square plus Z2 absolute square is less than 1, and the polydisk is just 2 copies of the disk, so it's Z1 comma Z2 such that Z1 absolute comma Z2 absolute less than 1. So now it's very clear that the Euclidean ball and the bidisk, this is called bidisk, are simply connected. One thing I want you to remember, that is why I had done this in the very first class or the first lecture. The bidisk is actually a 2 copies of the disk across the disk. Now, consequently, from this to this, we can take what is called the Mobius map, phi 1, phi 2, of the form Z1 minus alpha 1 divided by 1 minus alpha 1 bar Z1, comma Z2 minus alpha 2 divided by 1 minus alpha 2 bar Z2. This will play a role afterwards. P1 comma P2 is of this form. Okay. So, so you can see that given, so this is going to be bijective because each P1 and P2 are bijective on this, and this is just a Cartesian product. These are bijective maps. And well, given any pair of points alpha 1 comma alpha 2 in the bidisk, this maps it. So this is any pair of points, this maps it to 0 comma 0. In other words, among all automorphisms of the bidisk, there is a set of automorphisms that acts transitively, meaning any arbitrary point goes to 0 comma 0. Anyway, so these are the things about the ball and the bidisk. Both, when n equal to 2, if you restrict, when you restrict to n equal to 1, both of them just become the disk. The question is, does there exist a biholomorphic map from the ball into the polydisk? Does there exist a P such that it's bijective and holomorphic? Now, when I say holomorphic, there is one last thing I want to say before I go on. A holomorphic map of a domain omega in Cn to Cn. So if I have a map from omega to Cm, I call it holomorphic. First of all, notice that any map that lands in Cm, f of z, z in omega, is going to look like f1 of z and fm of z. So this is what any function is going to look like, but each f1 through fm is a function of z1 through zn. And I call f holomorphic if each of F1 through Fn, Fm are holomorphic in Zi when the other variables are all fixed. Okay, so this is essentially saying that when you look at functions in n variables, you are doing nothing more, nothing less than saying that it will be holomorphic provided it is holomorphic in each of the variables separately. Okay. At this point, let me just again kind of pause a little bit and ask if anybody has any question. Is there anyone with a question or comment, or am I sort of, does any of this make sense, or nothing is making any sense, or what? One of you, any one of you can say something, or nobody has anything to say? It's kind of difficult to lecture with. So Rajesh, you think this space is okay, or I slow down, go faster, or what? What is your opinion? I guess.
I guess he's not.
Yeah,
I don't see him. I mean, he's there, but
yeah.
there's something wrong. I mean, your screen is only showing one page right now.
Saying what?
Something. Your screen is not showing the slide right now. It's just showing your.
Yeah. Because I am scribbling.
Yeah.
Yeah. Whatever I am scribbling, that is shown, right?
Yeah, it was. Yeah.
Right. No. I haven't gone into the slides. I just thought I will kind of explain a little bit before I go to the slides. But you think then we just continue, right?
Yeah, it will be. I mean, I think it's better if we can continue.
Yeah, right.
Yes, sir. Yes, sir.
Huh?
Yeah, sir. Continue, please, sir. It is interesting topic.
Oh, okay, all right. I'll just continue that. Okay, now we are back to the, my screen is visible, right?
Yes, sir.
Okay, good. So all of this is built up, as I said, just one thing I want you to remember is that holomorphic function in n variables is just holomorphic in each variable separately. So I look at a function in n variables. I allow n minus 1 variables to be fixed, and in the remaining one variable, it must be holomorphic. Each variable separately. And this we know. So these are basically holomorphic functions in one variable. Okay. So as long as a function is separately holomorphic, I'm going to say that it's a holomorphic function in n variables. All right. So as I said, for now, I'll skip what was left over from yesterday and go to hope that I'll be able to convey this idea of how how the bidisk and the Euclidean ball are not biholomorphically equivalent. That's a very, very interesting and surprising fact that, as I said, was already found by Poincare. And again, to tell you a little story, what I'm going to do before I get into the details, already yesterday, Deepak had talked about the Bergman space, and he will continue talking about this a little bit more later in the tutorial session. Given any domain omega in CM, there is what is always called a Bergman space, A2 of omega. And this is nothing but all holomorphic functions in omega such that absolute F square is integrable on omega with respect to the volume measure. Okay. This object is a Hilbert space. If you look at all these holomorphic functions, which are square integrable with respect to the volume measure, this forms what one might call a Hilbert space. Now, the discussion about the reproducing kernel and all that, what is more, this Hilbert space possesses a reproducing kernel usually called the Bergman kernel. And this Bergman kernel has tons of very desirable and very useful properties. So typically, if F is in what I am calling A2 of omega, for every F in A2 omega and little omega in capital omega, you have that F inner product with something that we will call the Bergman kernel. So this is the variable which I am not writing. B dot omega. Well, okay, let me not write. Just inner product I will write. So then I don't have to write. Yeah. This inner product is actually F of omega. Okay. So this, if you like, F is a function of some variable. B omega is a function. So this is in the Hilbert space for every fixed omega, fixed but arbitrary omega, B omega dot omega is an element in, this is an element in A2 of omega. So omega is fixed but arbitrary. B omega dot little omega is an element in the Hilbert space. You take its inner product with F, what you get is F of omega. This is like your Cauchy, if you like, and if you want to make a connection, this is like Cauchy integral form. Should remind you of the Cauchy integral form. Okay. So this is so much preaching for today. Let us start formally with so what happens is that given a reproducing kernel Hilbert space, this is again one last thing I want to say. This is something that Deepak will discuss today in the tutorial session. Given a Hilbert space with a reproducing kernel K, pick any orthonormal basis. Let En be any orthonormal basis in H. Then K, Z, comma W, as was discussed yesterday, you know that this reproducing kernel is a function of two variables. It has an expression of the following form: E and Z, E and W bar, n equal to 0 to infinity. There are a number of things about this. This makes sense. It is convergent for every fixed W. This is an element in the Hilbert space. In other words, if you fix the W, then this sum, summation E and Z, n equal E and Z, E and W bar for every fixed W is an element in the Hilbert space. So the convergence is a convergence in the Hilbert space, but there is more. It actually converges as a complex function in the uniform topology on compact subsets of the domain omega. So K, Z, comma W, if you want to compute this, you need to find an orthonormal set En. And that's what we do. Okay, so you want to find the Bergman kernel for the polydisk, and you also want to find the Bergman kernel for the Euclidean ball. Well, to find these two Bergman kernels, you have to find an orthonormal basis. And how do you find an orthonormal basis? Well, in this particular case, as Deepak had already started explaining, DM is the polydisk, which means that you are really looking at a product measure. And I will not go into the details right now, but it turns out because this is the product measure, you can actually essentially take the orthonormal basis one at a time and multiply them to get the orthonormal basis for the Bergman space of DM. What that means is the orthonormal basis looks like Z1 to the power I1, Zm to the power Im. First, you prove that whatever multi-index you pick, if you pick another Z1, J1, Zm, Jm, and if these multi-indices I1 through Im and J1 through Jm are not equal as multi-indices, then these two elements, these two monomials are actually orthogonal. And then all that remains for you to do is to find what is the norm of these elements, these monomials. And that norm, I am telling you right now, is this quantity, Ni plus 1 product square, okay, where this Ni is the what is Ni? This is not Ni. It should have been Zi product Ni I equal to 1. The length. This is the multi-index. So it should have been. It's actually, how should I write it? I sub k. It should have been I sub k, k going from 1 to n. Okay. This n is usually something that one thinks of generally as the multi-index. So that's why that n has kept in. This should have been I sub k plus 1. Okay. Product square root. And similarly, this will be also I sub k plus 1, product k equal to 1 to n, and then sum mod I equal to 0 to infinity. If you do that, the main point is the answer for your Bergman kernel would be the Bergman kernel of the disk, but multiplied m times. Okay, so you'll get for the first copy of the disk, the Bergman kernel is 1 minus Z1 W1 bar to the power minus 2. The second copy will be 1 minus Z2 W2 bar to the power minus 2. It will go like that. The product 1 minus Zm Wm bar Zm Wm bar to the power minus 2. Okay. So this is just the product of the Bergman kernels of the disk separately, and you take the product and you get what is called the Bergman kernel for the polydisk. But as I told you, to compare whether the ball and the polydisk are biholomorphically equivalent or not, we have to find the Bergman kernel for the Euclidean ball as well. For the Euclidean ball, you have the same situation in the sense that Z1 I1, Zm Im, and Z1 J1, Zm Jm are orthogonal. Okay, as long as I1 through Im is not equal to J1 through Jm. So these two monomials are orthogonal. All that remains for you to do is to find out what's going to be the what should I say? What's going to be the norm? What's going to be the norm of such a monomial? That norm, if you look at yeah, here it is written. If you look at Z to the I, where the length of I is actually, again, I think, length of I is varying from 0 to infinity. The norm of such a monomial, as is written here, minus m minus 1. You might wonder what that means. I'll tell you in a minute. This binomial coefficient times the length of this multi-index, choose I. This is a multinomial coefficient. N choose I1. This n is mod I. Okay, In. So this is a multinomial index, multinomial coefficient. Minus m minus 1 mod I is actually mod I plus m. Actually, there is a standard thing for that, which is if you have minus n, choose k. What you do is you write k plus n minus 1, choose k. That is what is the meaning of this this binomial coefficient. So once you put that binomial coefficient in, what you find is that you have an explicit expression, the Zi. I mean, everywhere there is a square root. Here also, in what I wrote, there is a square root. So, so if you write this expression is nothing but Ei. The orthonormal basis is Eiw bar sum. Okay. So the orthonormal basis is Eiz equal to Z to the power I, except there is some coefficient here. This is an orthogonal set as I varies in all multi-indices, but it has to have a coefficient to make it a norm or a vector of norm 1. That is where the integral with respect to the volume measure comes in. But if you do all this calculation carefully enough, and this is given in complete detail, all the details have been worked out in many places, but in particular in Crunch. Several complex variables. Both of these computations are in this book here. And here, for the Euclidean ball, the Bergman kernel is 1 minus ZW inner product to the power minus M minus 1. Okay. Now, okay, so that's so much for the Bergman kernels, specifically for the Euclidean ball and the polydisk. Actually, some of these computations will not be necessary as explicitly as I am giving them here, except at the very end. And that too for M equal to 2. That is the case where we'll say that these are not biholomorphically equivalent. All right, now we go back to some generalities. So these were just the examples of Bergman kernel obtained by using the formula EIZ, EIW bar summed I, I such that mod I equal to 0 to infinity. Okay, so you do overall multi-indices, and we saw that in one case, in the polydisk case, this is so there were two answers, 1 minus Zi Wi bar to the power minus 2 product I equal to 1 to M, and in the other case it is 1 minus Z inner product W to the power minus M minus 1. Okay, these are the two Bergman kernels. If you put M equal to 2, here there will be only 2 factors, and here this will become a power minus 3. But now let us talk about generalities. One of the general things that I want to discuss is the biholomorphic map. Suppose you have 2 domains and you have a biholomorphic map from D to D tilde, then I claim it induces a unitary operator from A to D tilde to A to D defined by this formula. Now, I want you to remember that this formula, again, it can be thought of as what one thinks of, think of this as the change of variable formula. Or integrals. Okay. Now, as many of you know, the way to do it is to say that if you look at f composite phi and you want to integrate, just as in one variable theory of integration, you want to integrate this over omega, starting with over omega, but you want to relate it to integral over omega tilde. Well, phi is going from omega to omega tilde. That is why f composite phi, you want to relate it to integral over f. Well, to relate these two things, all you have to do is to take this and multiply it with the complex Jacobian of phi absolute square, and then this will become this. I mean, here I am using the volume method. What I mean by that is that if you have a phi that maps D tilde to D to D tilde, which is biholomorphic, then to find the integral of f composite phi, you have to adjust the volume measure. Essentially, what it means is that the volume measure in the domain D tilde is related to the volume measure V in D by this determinant of the Jacobian. As many of you might have seen in your ordinary calculus, the determinant somehow, determinant of the derivative sort of represents the, how the volume transforms from one domain to another. So, so the change of variable formula for integration tells you that to go between two domains when you particularly have a bijective map, the adjustment that is necessary is via the determinant of the derivative. And this is where, again, I must emphasize, a lot of this is actually very, very detailed linear algebra, if you like. You think of phi, you look at the derivative, think of the derivative as a linear map, and then you look at the determinant and you see how the determinant transforms little parallel pipettes from one place to another. Okay. And then putting all that together, it's not an entirely trivial business, but finally you get a change of variable formula. There is actually, if I'm not mistaken, a very nice article by Kumaresan, which appeared perhaps in the newsletters of the Ramanujan Mathematical Society, which discusses this change of variable formula in some detail. This is not a entirely trivial business. Okay, let me point that out. But having said that, I want to, I mean, if you take the change of variable formula for granted, then defining this map F composite phi times the Jacobian. The Jacobian is my notation, if you like, for the derivative. So this is essentially the derivative. This is the derivative. Then, because of the change of variable formula, you see that F dV is F composite phi, this absolute square dV. Okay. Consequently, if you ask whether this is a unitary map, well, since phi is biholomorphic, that is bijective, this derivative does not vanish. This is bijective. Therefore, this map from A to D tilde to A to D is actually a bijective map. As a, I mean, it's onto and it is one-to-one because phi is one-to-one, and this Jacobian, this derivative, is non-vanishing. Because of that, as a set map, this is actually bijective. But there is more. Because of this change of variable formula, if you look at absolute F square integral, then you will get under this U phi, this absolute square JC phi absolute square dV. But that is nothing but UPF. So you conclude that UPF must be actually a unitary map. Okay. Therefore, if we have an orthonormal basis, this is an orthonormal basis. Give yourself any orthonormal basis in A2 of D tilde. Then, by applying this unitary map, you will get a new orthonormal basis in the A2 of D. So the new orthonormal basis is going to be what? Well, you apply, you take the element En tilde, apply U phi to that. That means you have En tilde composite phi. First you compose, then you multiply by the derivative. Okay. I mean the determinant of the derivative, not derivative, determinant of the derivative. So, so when you do that, this being a unitary map, the new object here this tilde should not be there. You are defining En to be j phi comma dot, which is the determinant of the derivative, times En tilde composite phi. That is the unitary operator. And that you are defining to be En. Okay. So from any orthonormal basis in A2 d tilde, you get an orthonormal basis in A2 of D. Now this means that the Bergman kernel has what one might call a transformation rule. Let us see how that works. So if you have an orthonormal basis, then the Bergman kernel looks like summation ENZ ENW bar. Okay. So the Bergman kernel B, which is of this form, there is one little thing that I have to say, which I did not before. When I say that the Bergman kernel or any other kernel for that matter is of the form summation ENZ ENW bar n equal to 0 to infinity, you might legitimately ask the question, if this expression were to depend on the choice of the orthonormal basis, we will be in real trouble. Choice of the orthonormal basis. Fortunately, if this expression, this entire sum, which I am calling the reproducing kernel, if this were to depend on the choice of the orthonormal basis, then we will be in real trouble. But fortunately for us, this sum defining the kernel does not depend on the choice of the orthonormal basis. So what I am going to do now is to say that suppose I had an orthonormal basis in A2 of omega, then En composite phi times the Jacobian multiplied by the Jacobian determinant J of phi multiplied by the Jacobian determinant. This is also an orthonormal basis, and therefore the sum obtained using this and the sum obtained using this are going to be the same, because the kernel does not depend on the choice of the orthonormal basis, and that gives what we call the quasi-invariance of the Bergman kernel. So the Bergman kernel is what is called a quasi-invariant kernel. All right, so let us see what does it mean if we write that down. Well, if we write that down, what it means is that if I have any biholomorphic map at all from D to D tilde, there may not be any, but if there was a biholomorphic map from D to D tilde, then I can play this game of saying I take the orthonormal basis En to a orthonormal basis En tilde by doing En composite phi times J phi. Well, if I do that, then the orthonormal basis of the domain D, of course, is just the sum. This is just the sum En Z En W bar. Whereas this is the sum En composite phi Z En composite phi W bar. but I have a Jacobian to multiply. If JPZ and JPW bar. But this middle thing, summed n equal to 0 to infinity, is nothing but the Bergman kernel in the image space. So this is the Bergman kernel. And I still have the JPZ that I have to take into account, JPW bar. So that is actually the transformation. Okay, that comes from the fact, I mean, it comes from the basic fact that the map F going to F composite phi times the Jacobian of phi, meaning the determinant of the derivative of phi. This map is unitary. Okay. So this is our basic transformation rule for the Bergman kernel. Now, according to the story that I have heard, let's see. There is another little thing that I'll have to say. Now suppose we take D to be D tilde, and suppose we have plenty of biholomorphic maps. From D to itself. So much so that any W or any Z in D can be mapped to 0 by some phi. Now remember, in the case of the polydisk, I showed you that given any alpha in the polydisk, there is a phi mapping dm into itself such that phi of alpha is equal to 0. The same property holds for the Euclidean ball as well. There are many other domains for which it is true that given an arbitrary point, there is a bijective holomorphic map that takes that arbitrary point to some pre-assigned point in your domain, fixed point, which we are assuming in this case is just the origin. So let us say whenever a domain omega has such a group of biholomorphic automorphisms, the domain is called, is said to be admitting a transitive group of biholomorphic automorphisms. So suppose D admits a transitive group of biholomorphic automorphisms. Okay. That means given an arbitrary point in your domain, there is always a biholomorphic map. By biholomorphic, I mean a holomorphic map which is bijective. Then if you go back to this transformation rule and you pick a PZ, so here now in this rule, D is equal to D tilde, and what you are doing is you are finding a PZ such that PZ of Z is actually equal to 0. So then what you can do is put Z equal to W. Put Z equal to W. So on the right hand side, you have just BD of Z comma Z. Left hand side, you have BD, but now you have put P equal to PZ. So this becomes 0. This also becomes 0. And this becomes Pz. Okay. So you find exactly this, that the Bergman kernel at z comma z is nothing but the determinant of the derivative of such a Pz, absolute square, the Bergman kernel at 0, 0. Now, I wanted to tell you a story from people who have witnessed this. They seem to know that Bergman, who is a Swedish mathematician, while working on this, when he discovered the Bergman kernel, he was hoping that the Bergman kernel itself will be a biholomorphic invariant. What would that mean? That would have meant that BD tilde Pz comma Pz is actually equal to BD of Z comma Z. See, this way you could check whether D and D tilde are biholomorphically equivalent or not by simply computing the Bergman kernel for D tilde, computing the Bergman kernel for D, and say that if they were biholomorphically equivalent, then B D tilde Pz, B tilde D tilde Pz has to be Bz comma Z. Okay, so this way you would have to kind of be able to decide whether two domains are biholomorphically equivalent or not. So Bergman himself apparently was very depressed and unhappy when he found that the Bergman kernel, instead of being a complete invariant, that means instead of these things not being there, it is only what I have called quasi-invariant. Quasi-invariant meaning it's not quite an invariant object, but it's very close to being invariant. So, so he was rather unhappy, and I'm not entirely sure how this story goes. And this is what happens in mathematics when I tell you this. Again, like yesterday, I kept saying, you should be surprised. At this point, I would like to ask, what would you do if your life's mission was to find an invariant and you have come this close? You have come this close. You have something which is not quite an invariant, but is a quasi-invariant. But nevertheless, you kind of ask yourself, well, it would have been great if instead of it being a invariant, being a quasi-invariant, it would have been an invariant. So you ask yourself this, you walk up and down, but with hindsight, as I have told you, Bergman was very upset that the object that he spent years working on finally turned out not to be an invariant, but only a quasi-invariant. Now, I again want to stop here for a minute and ask you, unlike Bergman, we have discussed many things. There are lots and lots of things in front of you. You already have a lot of inputs, which perhaps Bergman did not have. And the story I was telling you, according to the friends of Bergman, he was rather depressed, unhappy, and it turns out finally, after many years of effort, he was able to make an invariant out of this quasi-invariant. Now, I want to ask, can any of you actually guess how to turn this quasi-invariant into an invariant? Any guesses? Any idea at all? How this might become an invariant? Or what manipulate? See, this is what happens in mathematics. When you see the answer, you would wonder why it should have taken many years to find such an answer, particularly by people who are already, experts or well versed with the mathematics of this. Okay, so let me then stop, bothering you. Let us continue then. Okay, question is, what is the invariant? Well, we have already seen a curvature before. That is why I was telling you, unlike Bergman, perhaps you have the inputs and you should be able to say how this goes. Now, the quasi-invariance of the Bergman kernel also leads to a biholomorphic invariant for the domain D. That is what now I want to explain. Well, we are in more than one variable. Yesterday, when I was talking about the curvature and so on, we were talking about only objects in one variable. Just for the record, the way the curvature is written is not quite like this. What is written is d square dzi dzj bar and log of this dt z comma z. So far there is no problem. Ij equal to 1 to m. But here for those of you who don't want to worry about this, it's no problem. This is what is called a 1-1 form, and the very strictly speaking, the curvature that occurs in complex geometry is actually a 1-1 form, and it's of this form. But to keep our exposition simple, I'm not going to worry about this. It really doesn't matter. Again, just to be strictly correct, I wanted you to know that the curvature is actually a complex 1-1 form, holomorphic and anti-holomorphic. One holomorphic, one anti-holomorphic. But I don't care about that. For our purposes, it is enough to look at this M by M matrix. The M by M matrix has the great advantage that you can take a determinant of this matrix. Okay, the determinant has already occurred before. What we are claiming is that, okay, you have this object and you also have this object, the Bergman curve. Now, this is a matrix valued function. But if you take the determinant of it, it will become a complex valued function. The ratio of this complex value after taking the determinant, the ratio of the determinant of the curvature by the Bergman kernel is going to be an invariant for the domain D. Somebody trying to say something? Did anyone ask a question or say something? No? Okay. So remember, the reason this BD did not work, was because it had this stupid determinant of the derivative. Now, what I want to do is to say, well, when you plug in BD and when you plug in pz comma pz. Actually, I should have written z comma z. It's actually two variables. Then there is a j of phi and j of phi bar that comes out. Okay. Only this will become bd z comma z. What I want to do is to say that if my k was such that when I take the determinant, that also transforms according to the same jp and jp bar, what will happen is the jp and jp bar from the numerator and jp and jp bar from the denominator will cancel out. And consequently, this will become an invariant. That is the whole idea. Okay. That is how. So that means we need to find. This means we need to find a transformation rule for the curvature of BD. Now that's not very hard to do. Again, it's there in many places, including some of the things that you will find, in the book of Cranch, it's there in many places. But I'll tell you what happens. Okay. So, when you, rather than looking at the general phi going from d to d tilde, what I'm doing here is to say, for our purposes, it is enough because we are looking for biholomorphic invariants. Let's first look at the special case where you have a biholomorphic map from d to d. And then we have already discussed that this map, which is multiplication by the Jacobian, that is the determinant, times F composite phi, is already a unitary map or a unitary linear transformation on the Bergman space. Okay. Now this J that we have, actually this is not very important for what we are doing. This is just some ancillary, some digression. This derivative that we have written down, if you think of it, this is a derivative. It has two arguments. One is the phi, the other is where you are evaluating. Now it satisfies what is called the cocycle property. And the cocycle property is nothing but something like the chain rule for the derivative. This is just the chain rule for the derivative. This, as I said, is a bit of an aside. Okay, which means just this. When you take psi phi, this is a composition, then the derivative of a composition is the derivative of the first function evaluated at the value of the second function times the derivative of the second function at j. So this makes the map phi going to u phi, this property of being a cocycle or having the chain rule makes this map a homomorphism. So all in all, u phi is a unitary and this map is a homomorphism. Therefore, whenever you are looking at the group, this OT D, the set of all automorphisms of the domain D, which are bijective, automorphism of course bijective, the holomorphic bijective maps of the disk. From that to unitary operators on A to D, the Bergman space, you always have this phi going to u phi is a unitary representation. Okay, this is an aside. This is not really so important for now. Okay. Now we come to what I promised, namely the change of variable formula for the curvature. This, if you look at Rudin, function theory on ball, on the ball, you will find he has written down a change of variable formula for holomorphic functions in so many variables. Okay, it's on page 17, 18, something like that. So please believe me that if you just use the change of variable formula and nothing more, what you will find is that this curvature at PZ PW, again here there is a slight typo. I mean you could say the I mean I have polarized here. If you look at, we can put at the end Z equal to W, which will be actually the curvature. We have to put Z equal to W. But before putting Z equal to W, we can do D square dzi dwj bar log of the kernel function. Okay, and using this change of variable formula from Rudin, what you will find is that this is the same as pulling out the derivative of the function phi. Here, this will come with a transpose. If you carefully look at this I, L, L, K and all that, this is actually the transpose of the derivative of phi. This is the conjugate of the derivative of phi. And here there is a typo. This phi should not be there. This is just log of d square dZL dwk bar log bd evaluated at z comma w. But because you are evaluating only at z comma w, you have to compensate by multiplying with the derivative of phi and conjugate of the derivative of phi. This is the transpose of the derivative of phi. This is the conjugate of the derivative of phi. That is nothing but d square dzi dwj bar log of bd tilde. Okay. So this is how the transformation works. If you want to write it without this matrix form, as I said, and here it is written correctly, the curvature, which is actually this di, dj bar, log and all of that. So this is the curvature at pw, comma pw of the domain d tilde in the image, adjusted by the determinant, not the determinant, here the full derivative of the function phi but transpose, derivative of the function phi with a transpose times the derivative of the function phi with a conjugate is actually equal to the curvature of the original domain D. That's the transformation rule for the curvature. Now, remember what I told you before, to form an invariant. So the curvature transforms with the full derivative, one with a conjugate, the other with a transpose. However, the kernel transforms with the determinant of the derivative conjugate and the determinant of the derivative. Okay, this is the full derivative. This is a matrix valued function, but this is a scalar valued function. Now we are in good shape. Yeah. Now we are in good shape, taking determinant on both sides of what? Taking determinant on both sides of this expression. Remember, I have been repeatedly saying that this is a matrix valued function. So this is a matrix. I can take the determinant. I can take the determinant here. I'll get a product of 3 determinants. Okay. So the determinant of the curvature is the determinant of the derivative, the determinant of the curvature again, determinant of the derivative. Okay. So taking the determinant, we get this. Okay. But then we are in good shape because we get the ID object that we had defined before, namely determinant of this divided by determinant, I mean the curvature of this guy, sorry, the Bergman kernel, is exactly from here is the Jacobian, that is the determinant of the derivative absolute square, determinant of the curvature divided by the Bergman kernel. Okay. Well, but that's the same as apply the transformation rule for this guy, then you find that that's the same as the determinant of the derivative absolute square and the Bergman kernel evaluated at PW, PW. But main point is this determinant and this determinant cancel out. Okay, leaving you determinant of the curvature at PW, PW divided by the kernel at PW, PW. That means that when you look at a quantity like this and replace the W by PW, here and here, nothing changes. You get the same answer. That's exactly what an invariant is all about. So for any homogeneous domain D in CM, the function IDZ. Now, this is true that ID is an invariant, but if you had a domain such that there exists a map, such that there exists a map taking an arbitrary alpha in D. So if that happens, then this quantity is actually a constant. Okay. So now we finally prove that the Euclidean ball and polydisk are not not biholomorphic. So the proof that whenever you have a homogeneous domain, ID is a constant is easy to see, because you take ID at 0, then that is by definition this quantity. But then you have a automorphism that takes 0 to an arbitrary point U. So you pick that PU, you know that this quantity is the same as any P that you apply to 0. So apply PU. If you apply PU, this and this have to remain same. But PU at 0 is U. This is also U, but this is IDU, where U is an arbitrary point in the domain D. So whenever, as I said here, whenever there is a P taking an arbitrary point alpha to 0, which is what I have used here, that PU, there exists PU such that PU of 0 is equal to U in D, where U is arbitrary. So using this, we see that ID at 0 is the same as ID at U, where U in D is arbitrary. Okay. So consequently, not only we have an invariant, but the invariant is actually a constant if you have a homogeneous domain. So in the end, I want to say, if you look at the bidisk and the Euclidean ball and assume that they are biholomorphically equivalent, well, on the bidisk, I have already shown you that there is always a P1, P2 that maps 0, 0 to any alpha 1, alpha 2 that you want. But if D2 is biholomorphically equivalent to the Euclidean ball, then the Euclidean ball, after composing with this biholomorphism, will also be homogeneous. Okay, whatever that means, let's not worry about that. It turns out that even on the Euclidean ball, you can see this directly if you like, but it will follow from here, that the Euclidean ball is also homogeneous if you assume that the bidisk and the Euclidean ball are biholomorphically equivalent. Well, then we have come to the wonderful conclusion now that to decide whether the bidisk and the Euclidean ball are biholomorphically equivalent or not, we have to simply compute I of the ball at 0, and we have to compute I of the bidisk at 0. It turns out one of these is 4 and the other is 9, as I have said here. And of course, we know 4 is not equal to 9. Therefore, we have arrived at a contradiction if we assume that the bidisk and the Euclidean ball are biholomorphically equivalent. Okay. So there are a bunch of other things that have to do with unitary representations of the automorphism group. In any case, I'll not remove that from these slides. I'll neither remove these last few slides, which talks a little more about the unitary representations and such, nor would I remove the leftover part in the beginning. So I'll upload the slides to the Dropbox. And thank you very much. We will perhaps see you during the tutorial in the afternoon at 2:30.